Hey everyone, this is Abhinav from Confessions of a Code Addict. Have you ever been in a situation where your boss comes to you and asks you to optimize the performance of a piece of code that you think you have already, reached to its full potential, like you don't even know from where this 2x performance is going to come now. So in this video, I'm going to show you one performance trick, which is relatively obscure. Very few people actually know about it or talk about it, but it can actually improve the performance of loops by 2x or even more. So specifically, we are going to talk about the decoded stream buffer in Intel microarchitectures. So it is a specific buffer in the Intel processors which is designed to optimize the execution of loops or frequently executed code paths. But it it is specifically designed for certain code patterns and only certain conditions under which it is used by the processor. So now, to ensure that those conditions are true or they are met, your code has to be laid out in memory in a specific way to meet those conditions. And that depends on how you write your code and also how the compiler optimizes your code. So it all comes down to understanding the microarchitecture of the CPU, what kind of optimization, what kind of code your compiler generates, what kind of optimizations you can make it do, what are the tricks that you can do to force the compiler to optimize for using this buffer in the CPU. So what we are going to do in this video is we are going to first debug the performance of a program using Linux perf to see that particular program has a bottleneck in the DSP. So we will use Linux perf. So we'll learn to use Linux perf in this video to identify these kind of hardware level bottlenecks. And once we have done that, we'll talk about some of the compiler tricks that we can do to force the compiler to optimize the layout of the code so that it actually takes advantage of the DSP. Yeah, so that's the overall outline of this video, and this is going to be very exciting and going to be a very deep dive into the microarchitecture, Linux perf, compiler, and all of that. So yeah, so let's get started. So I'll start by first showing you the program that is slow. So the program is this. So it is a simple program that takes two numbers as command line arguments and it computes their GCD. So this is the program. So we are using the str2l function to read the command line arguments, converting them to long values, then passing them to this GCD function, which is where the algorithm is implemented, and the overall performance of this program depends on the performance of this loop. So this is the Euclidean algorithm for computing the GCD, and we want to optimize its performance. So that's the goal. So what I'm going to do is compile this and run it. So I'm using the -O2 flag to GCC, which will do various optimizations on the binary. So it means that the compiler has already tried to optimize as much as it can. And if we run this program with these two specific inputs, let's see how much time it takes. So I'm using these two specific inputs because these are two very, one value is very large and one is small, which means the algorithm will take a large number of steps to converge, which means the program will take a large amount of time to finish. So we see that it took 5.16 seconds to run. And perfstat gives us some other information as well. So perf is a Linux kernel tool which integrates with the kernel, and it can be used to program the hardware counters in the CPU. So the CPU has certain number of hardware counters that can be used to capture the event count in the hardware. So certain hardware level events. So like for example, here we are seeing number of branches that the program took, the number of branch misses that happened, number of instructions, number of cycles, page faults, all of that. So these are captured using the hardware counters. So that is why I'm using perf here. So just to get an overall picture along with the time. And I also want to show you the actual optimization that we will arrive at the end of this video, because that will just show you the payoff. Like a single line of code, we'll by the end of this video we'll understand what this line of code actually means. But for now, let's just see. So I'll recompile, I'll run it again, and what we are going to see is that this program now runs 2x faster. So it just took 2.66 seconds, which is almost 2x faster. So the number of cycles that the program consumed was reduced by half to just 10 billion cycles versus 20.5 billion. So yeah, so you can see the impact of a single line of change. So that singular line of change actually ensured that the loop was cached in the DSB. So I'll talk about the DSB and all of that. But how do we figure these kind of bottlenecks, and then how do we figure out these specific optimization? For that, we have to learn to use perf, and how we have to understand the microarchitecture. So what we are going to do is we are going to debug the performance of this slow program using Linux perf. So now perf we saw already. Perf start, if you run, you will get a bunch of default event counts on the CPU. You can also specify a specific set of events to perf. So by using -e and specifying a comma separated list of events that you want to measure. So here I specified just cycles and instructions. So it just captured these two events. So you can specify your own events. And how do you know which events you can specify? You can run the perf list command. When you run that, it will list all the available set of events that you can measure. So this list is quite long. It can be hundreds of events, thousands of events. It's pretty detailed, and knowing what exactly do those events mean and which one do you want to use to measure the performance of this program is very hard. Like without knowing it, without having a system, it is very hard to debug performance issues. So what we are going to do is we are going to learn about the top-down analysis technique. So it's a technique to do a systematic performance debugging at the CPU level, which was designed by Intel. So let's first understand what is this top-down analysis. So basically, our goal is to understand